Hi, this is Josh, and this is Tutoring Calculus Level 1 for a student presented with the following problem. We have the function f of x equals sine x, and we restrict the domain so that we see two wavelengths from x equals negative 2 pi radians to 2 pi radians. And you can see it here graphed on the right of the screen on Desmos. That is the sine wave going from negative 2 pi to 2 pi. The next thing we can do is we can actually plot a point here that's moving at a comma side a. Here, I'll label it here at negative 2 pi comma 0. And a is a slider. So if I hit play on the slider, you can see that a moves down the string. It's animated. It's that blue dot there. And then when it makes it to the end of the string, it will go back to the beginning because I have it on a sweep mode going from the left to the right. And the next thing I'm going to do is, because I want to track it, but also I can use the circle formula, x minus h squared plus y minus k squared equals r squared. And I'll set it so that it's tracking that same point, a comma sine a. So I have to offset x minus a squared plus y minus sine of a squared equals 1. And now I have a locus of points equidistant, radius 1, away from the point on the wave. Okay, next, the student was told for this assignment to draw the tangent line to the curve. And as an exercise, the student used the limit approximation of the derivative. And then we discussed it, and what you will learn formally in Calculus 1 class is that, yes, the first derivative is in fact the cosine of a. So if the function is the sine of x, the first derivative is the cosine. So that'll be the slope of the tangent. So then we can set up this linear equation of the tangent line, which will be y equals mx plus b, which will have slope cosine a times x offset by a, depending on where we are on the string, plus the sine value, f of a. We can see that here, that if we do this properly, then the line will, right, this is like point slope form. The line will have the proper slope. It will always be the cosine. But it also has to, at the same time, have that slope, but also intersect the point a sine a as it varies along the slider here. Furthermore, for the animation, it's a little bit distracting that that purple line goes on forever and ever. So as we discussed, what if there was a way to shorten the line so that it was always the same length, but it was like within that viewing circle here? And the way I did that was with this following restriction on the domain. Okay, as you can see here now, you can see that it looks like the diameter, which is 2, is never changing because we know that the circle has radius 1, so the diameter is 2. So that blue line contained in the circle is the tangent line with slope cosine, but it's been shortened so that it's contained within the circle itself. And I did that with this following domain restriction, which is a little bit more complicated than just the sine wave. You take whatever x value is being tracked, and then you make sure that it's between this component and this component, which is actually just the x component of the reference triangle. And let me explain here with the following picture. Okay. So if you just think about that black circle that we're just looking at, we know that the slope is the cosine, meaning that the rise over the run is the cosine. So we write that as the y component is cosine, and then the x component is just 1, because anything divided by itself is just the thing. Cosine a equals cosine a over 1. But now we have a reference triangle, and we need to find the hypotenuse, which would be the radius. So we do the Pythagorean theorem. 1 squared plus cosine a squared, and that would be the hypotenuse squared. So taking the square root, the hypotenuse is 1 plus the cosine of a squared as a goes through its wave cycle. However, what we want to make sure that the hypotenuse is actually 1. So take all 3 sides and divide by the square root of 1 plus cosine a squared. Now the hypotenuse is 1, and the base side, which is what we need for the delta x, for the change in x, will be 1 divided by 1 plus cosine a squared. So this is actually what's getting longer and shorter as it goes through its wave cycle. Okay, and as the tangent line it has this ever-changing slope. So again, what we did was we took what we knew that the slope will always be cosine A, it'll be varying. We figured out the value of the hypotenuse and then divided everything by that hypotenuse so that we now have delta y and delta x properly scaled so that the hypotenuse is always 1. Since the center of the circle is at point A comma sine A, we would track the x component change on the right side as being a plus 1 over the square root of 1 plus cosine a squared. That should say squared. And the y and the other radius, which is tracked this way, is subtracted from a. So this radius has the x component that is precisely a, which is the center point, minus 1 over the square root of 1 plus cosine a squared. So going back to the animation here in this overlay, that's precisely what I did for the domain restriction. Here you can see the domain restriction that gives us exactly 2 wavelengths, but here's the domain restriction for this long line so that it's contained within a circle so that that blue line is always like a ship of distance 2 as it goes down the wave. In fact, if I turn the black circle off, because that's just the way that I use the unit circle to find delta y and delta x, and then scale it properly, there it is. That would be like the ship's hull or the ship's deck bobbing up and down as it goes through a wave cycle, okay, with the proper changing slope. As you study more calculus, you'll know that the slope varies just like the cosine function does between -1 and 1, right? It's just going up and down, and there it is. All right, so I hope this was a useful video for you in coding for Calculus 1 class and using animations and sliders such as this excellent tool Desmos. Thank you for watching my video and happy studying. Bye-bye.